So if you look at these property charts, Young's modulus versus density, and we'll take the case of, in this case of aluminum alloys or steels, right? You have e to the power half divided by rho as a material index for the beam, right? And effective material properties as E by phi and rho by phi, and then if we went ahead with that, we could get those kinds of efficiencies. So as you go to very large and very complex structures, you can exceed that initial estimate that was provided as a maximum. Let's go to the opposite extreme. We have seen that nature, especially during midterm 1, we have seen many examples of this, where in nature you have these complex shapes. They are able to perform extremely well in terms of the load that they carry, the stresses that they see, and ability to synthesize them from immediate surroundings and without consuming a whole lot of energy. Let's try to apply these shape factors to the micro scale or even below, right? Let's take a look at, for instance, structures such as these, which can be extrapolated to a bunch of parallel tubes. We have, in the first half of the course, seen that we can evaluate the shape factor for stiffness limited designs in bending for tubes. So if you knew the diameter and you knew the thickness, you would get a shape efficiency factor of 3 by pi times r over t when r is very much bigger than t, right? As in this case. And so if you know r and you know t, we know how to be able to compute this shape efficiency factor. In order to do that, the area is given as 2 pi rt. The moment I is given as pi by 4 times r to the power 4 for the outer radius minus r to the power 4 for the inner radius. And this can be approximated to pi r cubed times t. Phi is then the stiffness for the shape in consideration, in this case, this particular circular tube, divided by a reference shape, which we take it as a square cross-section of equal or equivalent cross-sectional area. And at that point, you can get the phi shape factor to be estimated by 12i by a square. So now that for this particular shape for the tube, we have the shape efficiency factor of 3 by pi times r over t, we can go ahead and get the solution, right? So the previous information was just as a refresher, and you estimate the shape efficiency factor to be 12.5 for this tube. What if instead of having a tube that is 100 millimeters in diameter, what if we reduce that radius to 0.1 centimeter? That is 1 millimeter. And the thickness is reduced to 0.001 centimeter. And now we want to be able to consider a bundle of these tubes, let's say placed together as this hexagonal cell over here provided by this architecture.